part of the chapter, we're going to talk about what we call determinate versus indeterminate force systems and the application of the V-bands and steps when we do steps between teeth. And then we compare the segmented versus fixed orthodontic appliance, which is the continuous one. As you know, the laws of equilibrium require that for every force there is equal and opposite reactive force, Newton's law. And also, if you want to have a balanced body or a system, any force system, the sum of moments and forces should be equal to 0. So in other words, moments as well as forces generated by orthodontic appliance must be balanced in all 3 planes of space to have this body in balance. What happens when we do our continuous fixed orthodontic appliance that is attached to many teeth? The outcome in this appliance or this force system is unexpected and unpredictable or non-predictable. So basically, the outcome will be that we will have unwanted tooth movement and undesirable results. For example, if you have extrusion and intrusion and you want to achieve intrusion, most of the time we use extrusion plus intrusion, sometimes mainly extrusion, because our mechanics are complicated in a way we can describe them as indeterminate mechanics or indeterminate force systems. So what's the difference between determinate and indeterminate? Determinate if moments and forces can readily be discerned, measured, and evaluated. So if you can measure the moments and the forces in your force system, then you can consider this as determinate. If you can't do that, then it's called indeterminate. Maybe in such system, the indeterminate one, only we can predict the direction of net movements and approximate net force levels, but not the exact force that is felt by the two, for example, the 2 units of the system. Like mainly in the next or in this part of the chapter, we are going to talk about 2-unit system. We have posterior teeth versus anterior teeth. The anterior teeth, all the teeth together will be considered as one large tooth, and the posterior teeth also will be considered as one large tooth, and then we see how they react when we apply force system between them. So in such force system, you can tell if it's indeterminate. You can tell the direction of the net movement and the approximate net force. However, the amount of tooth movement felt, or the magnitude of tooth movement felt by anchor teeth and the teeth to be moved, which are the anterior teeth, for example, are difficult to determine in such system. That's why we call it indeterminate system. Another thing, example, like just to make it easy for you, so when we plan intrusion and extrusion, intrusion of anterior teeth and extrusion of posterior teeth, the results will not depend on the direction of movement, but it depends mainly on how much force will be applied in the system. Because if we apply for every action, there is equal and opposite reaction. So if we apply 40-gram intrusive force, this force will be felt by the posterior teeth as 40-gram extrusive force. So knowing the exact force felt by the posterior teeth and the anterior teeth will make your system predictable. Other than that, it's not predictable. It's not determinate. It will be indeterminate. This is the difference. So, for all practical purposes in orthodontics, The determinate system is described as the one that has couple on one side and only a force on the other side, no couple. For example, if we have intrusion arch between molar and incisors, to make it determinate, you have to have the wire inserted in the posterior molar tube, and inserting wire in posterior molar tube will create couple. So we have one end as couple. The other side, you don't have to engage the wire in the brackets, because if you engage rectangular wire in the brackets, this will create a couple. So instead, you have to insert stabilizing arch wire on all the brackets of the anterior teeth, and then you tie the wire that is the intrusion arch over this. So you'll have only one point contact anteriorly, and this will create one couple, what we call one couple system, which is determinate. If you insert the same wire into the bracket of the anterior teeth, so you'll be having couple posteriorly and couple anteriorly, this will create a two couple system. Then this is indeterminate system. I mentioned this is an intrusion arch. It's a wire that is inserted between molars posteriorly, first molars, and anteriorly the incisors, lateral, central, central, lateral. To activate it, what we do the V bend here, which will raise the anterior arm up into the vestibule. So if we tie it over the wire, a base arch wire, we insert base arch wire in the bracket of anterior teeth, we make them as one single unit, and then tie this wire over it, then this is one couple system. So this is determinate system. Can we measure the force here? Yes, we can, and the direction and the movement, everything we can measure it here. So let's try to do that. If we have this V bend now, the anterior part, as I said, going to go up. So to activate it, you bring the anterior portion down and tie it. So if you tie it here, as measured, we can measure that by using gauge, and we use the gauge to bring the anterior segment down up to the level of the brackets. There we see the force. The appropriate force to do this has to be 40 grams of force. So when we bring this down, we activate it, this will create 40 grams felt by the anterior teeth as intrusive force. Because this is balanced system, the posterior teeth will feel the same amount of force. And because we have two molars posteriorly, one on each side, each one of them will feel 20 grams of force. The distance between the anterior segment, the anterior tie, the anterior attachment of the wire, and the molar tube is about 30 millimeters. So activating the wire down will create a couple or a moment, which will be, as the arrow indicating, will be clockwise. In this view, it will be clockwise. And how much it is? It's about the distance from the anterior attachment, 30 millimeters times 20 grams, that will be felt by only one side, which will be the total 600, because it's moment we call it 600 gram millimeter. And anteriorly, so with this system, we expect the molar to tip back. This is the tip back example, similar to tip back bend. Anteriorly, if you look at this giant tooth, the four incisors together, their center of resistance will be here. Tying this wire anteriorly at the level of the brackets as an intrusive force, this will create a moment equal to the force, 40 grams, times the distance between the bracket and the center of resistance of this giant tooth, which was calculated to be 5 millimeters. So the anterior teeth will experience a flaring effect or counterclockwise moment in this view مقداره كم? How much is it? It's about 200 gram millimeter, because 5 times 40. At the same time, because the molar will extrude and the molar tube is away from the center of resistance of the molar, because from if you look at the molar from anterior view, from this view here, you can see that the molar tube is buccal to the center of resistance by around 4 millimeter, for example. So if it's 4 millimeter, then we expect the molar to experience another moment which will tend to tip the molar lingually, because it's away, the force application is away from the center of resistance by 4 millimeter. So if it's extrusive force, the tooth will experience lingually directed moment. مقداره كم? How much? It's 20 times 4. It will be around 80 gram millimeter, which is here. And this is just explain to you how you can measure the force system in general. So to make force system determinate, or what we call one couple system, it has to be like a cantilever spring or auxiliary arch wire placed posteriorly to molar tube, where we'll be having the couple, and anteriorly is attached or tied to a group of teeth at single point of force application. This will create a one couple system. Usually, like in practice, when we do that, because we know now that the posterior teeth will experience this amount of force with one couple system, so most of the time we try to reinforce our anchorage posteriorly. How? Either by adding lingual arch or palatal arch to hold the two teeth together, and also we can add second molar and premolars to make them as a larger unit. In this way, you will distribute the force over more units than if you have only the first molar tied to the system. So the most important examples for the one couple system, as we saw before, the intrusion arch and cantilever swing. What is cantilever swing? Its example for it is the one that we use to extrude impacted canine, and I'm going to show it to you in the next slide. So having cantilever spring between posterior segment like the molar and the canine will give you a long range of action with a minimal decrease in force as tooth movement proceeds. Why? Because you have long wire between the two units. Give you also excellent control of force magnitude. However, disadvantages of it that it's do not fail safely. So it will continue to apply force. So if it's distorted by the patient, somehow it might move the molar or the canine in a wrong direction. The other disadvantage is that the moment of force on an erupted tooth rotates the crown lingually as the tooth is brought toward the occlusal plane, because it's just two units. It's not part of fixed appliance. The advantage of our continuous arch wire is that it's all the teeth are tied together, so this will help to maintain the arch form most of the time, and we have our way of doing that, unless you have severely displaced tooth and try to bring it into the arch with an eye-tie wire, then you might distort arch form. So here's the same thing. When you try to bring the crown down, the crown might move lingually as the tooth is extruding. So this is undesirable. So with this cantilever spring, which is like a canine spring, extrusion spring, sometimes has disadvantages that easily can be controlled. So If we try to control it more and more, then maybe you have to add additional forces, which will make the system more complex, making it hard to know what the forces and couples exist. So maybe you can complicate it in a way that will make it indeterminate. The canine extrusion spring or cantilever spring. The same, similar to the previous example that I mentioned. It's a wire like made of, for example, rectangular wires, TMA wires. The best way is to use TMA wire. Why? Because TMA is the best wire to act as spring. It has long range of activation over a longer period of time. So if you want to activate the wire, of course, you will engage it in the molar tube posteriorly and then raise the anterior part of it and attach it to a bracket or button. A button. Why button? Because we want to do determinate system. We want to achieve, or we want to have one couple system. So the wire will be hooked over the button. So it will be touching the anterior segment, well, the anterior unit, which is the canine here, at one point. This will create one couple system. Upon activation, it was found that this force level is 50 grams, which is adequate to extrude the canine. So when you activate it, you raise the arm up. This will create 50 grams, similar 50 grams felt by the posterior tooth, because for every action, there is equal and opposite reaction. So the posterior teeth will have 50 gram intrusion force. It's similar. Here, because it's one side only, the force will be on only one molar, 50 gram and 50 gram. And upon activation, if you raise the wire up here, this will activate the the couple on the molar tube, which is in the range of how much? 20, the distance between the anterior unit and posterior, 20 millimeter, times the 50 grams. So the posterior tooth will feel 1000 gram millimeter counterclockwise moment in this view. So the roots will tip back in this system. And if you have no anterior teeth, the molar will tip forward. So the tooth will experience couple in the amount of 1000 gram millimeter. Again, the same thing happens here. If you look at the transverse, because you are applying the force on the buccal of the center of resistance, which comes in the center of the pulp. If you look at the tooth from the frontal view, this will create another moment that will tend to displace the molar buccally. How much it is? It's 4 millimeter, the distance from the molar tube into the center of resistance. 4 times 50 gram to create 200 gram millimeter moment that will tend to displace the tooth buccally. So in general, when you try to intrude any tooth, because you are away from center of resistance, because we apply the force on the buccal surface, then we expect, or the labial surface, then we expect the tooth to move lingually. And if we tend or try to extrude any tooth, because we apply the force again from the buccal, because we are away from center of resistance, which is in the middle of the tooth, then we expect the tooth to displace buccally. So this is a general rule you can apply on any extrusion intrusion force. I told you, so if you look at the system from frontal view, so looking at the cross section of the system, you can see that because when we applied only the 50 gram force upon activation, the 50 gram of force, intrusion force, because it's away from center of resistance by 5 millimeter, here he measured it 5 millimeter, so the total, the molar will experience clockwise moment in the amount of 250 gram millimeter, because 50 times 5. And because when we activate this, usually the molar, the canine, for example, in this example, the canine is placed lingually position. So if you want to activate the wire, not only to raise it up to hold it, you have to move it in. So you want to apply a force to hook it into the canine, which is placed palatally. So you'll move the wire in, as in this example. So when you move it in, this activation will create another moment in this view equal to the distance between the two units, 10 millimeter, which is measured here, times 50 gram of force. So this will create a moment 500 gram millimeter. In which direction? In the opposite direction. So while the tooth is feeling 250 gram millimeter this direction, which is due to the activation of due to the intrusion force in this view on the molar, there will be opposite or counterclockwise moment equal to 500 gram millimeter in this direction. So theoretically, the molar will experience the net force 250 gram millimeter this direction and another 500 gram millimeter in this direction. So the tooth will experience counterclockwise moment in the net amount of 250 gram millimeter, which will tend to move the crown lingually or palatally. But again, if we look at this system now, although it's one couple system, but because when we activated, we moved the wire in, we created additional force system in this system. So we made this system more complex, and maybe now it's becoming more kind of indeterminate system. Again, because we apply the force here when we try to extrude the tooth, this tooth, we apply the force away from center of resistance of the canine. Amount, how much? 5 millimeter away from the center of resistance of the canine, 5 millimeter. This will create another moment, the amount of 5 millimeter times 50, create 250 gram millimeter. This explains to you how much it is difficult to apply the force system. If you're not careful in measuring it, you might have undesirable tooth movement. For example, let's say the amount of force we use here was 50, not 50, was 70 or 80. You just activated the wire and then you didn't even measure it, but turns out that the force was a force applied 70 or 80. So maybe instead of moving the canine down, the molar might intrude and displace lingually significantly. So knowing now the amount of force felt by each unit and the direction of movement in 3 dimensions will help you to plan your case. So in case you want to use this to make it more efficient and to avoid undesirable tooth movement, maybe we can apply stabilizing arch wire between this molar and the opposite side molar. Or we can also add the premolars and the molar with one stabilizing arch wire. So we distribute the 50 gram of force or whatever force, intrusive force, on the 3 teeth instead of only molar. So this will reduce the amount of undesirable, or will reduce undesirable side effects that we expect on the molar. I hope this is clear. Maybe you can go and listen to this again and again, then you'll understand it. So basically, the other example for the one couple system, as I said, the cantilever swing, is the intrusion or extrusion arches, the same example that I explained before. So we have, when we do intrusion and extrusion, let's concentrate on intrusion arches. We have several examples of intrusion arches. We have the um, utility arch, which is well known, which is attached to the molars and anterior teeth with bypass part. We're going to show you this example. And we have bursted intrusion arch, just the plain one, 1725, for example, TMA wire, that is inserted on the molar posteriorly and attached anteriorly on the anterior teeth in a one couple system. So let's see how this is like how this works, the force system, and how it affects the anterior and posterior units. So here, the same example I showed you before. This is the molar, this is the tube, and the V-bend. So to activate this wire, you need to do V-bend here. In a TMA wire again, and then anteriorly, it will go up to measure the exact force. We want to measure the force. How much force we want to apply? We want to apply force adequate to intrude anterior teeth, but optimum or minimal that will not allow extrusion of posterior teeth. As you know, intrusion will require light force. So the lighter force we apply, the less extrusion and less tipping of posterior teeth will happen. And also, to make this system more precise, we can, if we by now we know the undesirable side effect or tooth movement to the posterior teeth, we can overcome it by several ways. As I mentioned, we can add premolars to it as stabilizing as one giant segment, and we can use stabilizing palatal arch for this example. So in A, when we activate it, we bring the wire down. So let's start by B. Let's start by B. So when we activate in B, we bring the wire down, tie it on the labial over the brackets. You can see either you tie on the wire if the wire is very rigid, or tie on the brackets. So upon measuring it, we decided that the force applied is 40 grams, which is adequate to intrude, because intrusion movement occurs mainly by light force. You need light force. And it's if you increase the level of the force, you will never have intrusion. You'll have mainly extrusion, which you don't want. So you tie this wire, the intrusion arch. That you can apply this, guys, in your system, as I said, that you bring the wire down and then attach it to the anterior, and this will create 40 gram felt by the anterior teeth. It will be distributed in the 40. It will be 10 gram for each tooth, which is adequate for intrusion. So I'm going repeating the first slide just for you guys to understand. At the same time, activating this will create an extrusion force on the molars that will be felt in the amount of 20 gram on each side, because we have two molars. At the same time, the posterior tooth will experience, because upon activation, the couple will be activated. You bring the wire down, the couple will be activated, will experience 600 gram millimeter moment. How did we measure it? We measure it by measuring the force, the distance between, they multiply the distance between the two units times the force, 20 gram to give me 600 gram millimeter. So, because the tie is away from center of resistance of the giant tooth, we expect this tooth also to experience a moment which is counterclockwise in the amount of 5 millimeter times 40, 200 gram millimeter. So expect the molar to tip back and the anterior teeth to flare. Let's say we don't want to flare the teeth. We don't want to procline in size while we are doing intrusion, because we know now the force felt by the posterior teeth and the anterior, and the direction of the force and the moment. So if we want to stop this moment on the anterior teeth, what do we have to do? we go back to A, instead of tying anteriorly, we can tie opposite to the center of resistance of this giant tooth. This will create no moment, theoretically no moment, because there's no distance between the center of resistance and the force application point. So by doing so, we expect, at least theoretically, to prevent the flaring or the moment, to overcome the counterclockwise moment that should be experienced by this tooth if we tie anterior to the center of resistance. There's another way to prevent this flaring effect is by cinching back. You can see here in B, you cinch back the wire. This was found to prevent flaring. However, because the tooth, the flaring effect will create another horizontal force on the molar, which will tend to move the molar mesially. So if you're not careful with your cinch, when you did cinch, you're trying to prevent the flaring. So to prevent the flaring, you are applying force on the anterior teeth that will resist this flaring effect. This will be felt by the posterior teeth, so we'll have a mesially directed horizontal force on the molar, which if you don't have premolar here, this might move the molar forward. In case we want to use the same wire to do extrusion, we can do that, of course, if you want to extrude incisors, but however, this is rare to use this utility arch or auxiliary wire, the intrusion arch, we make it extrusion arch, is rare. But if we want to do the same thing, it's not that critical as in case of intrusion arch. Why? Because in extrusion, we need higher level of force. So although we worry that posterior teeth might not be that stable, however, not that critical, will not be that critical. Just to summarize for you, now for one couple versus two couple system, we mentioned that to create one couple system, which is determinate, that in which we can determine the level of force applied or felt by posterior teeth and the amount of force felt by the anterior teeth. If we want to create it, we just do an intrusion arch or cantilever spring that is attached or hooked into molar tube posteriorly and attached to one point anteriorly, like tied over the bracket or on a button, not engaged in the brackets. This is if we do that, then we'll create two couple system. And this is our example that we're using in biomechanics, that we have two giant teeth, one anterior, one posterior, and then the wire between them. Although it's long span, but it gives us the idea about how the force system will work and how it will affect the two segments, anterior and posterior segment. The utility arch is an example. Utility arch by Ricketts is an example of two couple system, and it's been in use for a long time by Ricketts. Basically, it's used to do intrusion of incisors. Also has many other uses, like sometimes we use it as space maintainer. We can retrocline incisor, procline, extrude, and that's why they call it utility arch. And basically, the difference between intrusion arch and Ricketts arch is that the utility arch, which is Ricketts arch, has bypass, longer wire that bypass the occlusion at the area of premolars and canine, so it won't be distorted. Adding this wire helped to make this wire very flexible, to have excellent load deflection properties, which make it suitable for intrusion because you can control it to apply light force over a longer period of time. However, it's not one couple system. So based on our rule, it is indeterminate system. So it's difficult in most of the time to ensure that you're going to do intrusion. That's why the results is variable. Sometimes we do extrusion with zero intrusion. and sometimes we do. It depends on the level of the force. Because we cannot determine, we cannot tell how much force is felt by the anterior and how much force is felt by the posterior teeth. This is in the picture in A. This is the utility arch. So what we do, bring rectangular wire 1622, for example. Rectangular because it's made of rectangular wire to give more control, and then you activate it by making V bend here. The anterior segment is engaged in the brackets directly. This makes this design as two couple system. So this is, if it's disengaged, so you raise it up, engage it in bracket, this will activate the system. You will have intrusive force on the anterior and extrusive force on the posterior teeth. Because posteriorly, exactly the same as in intrusion arch. The posterior tooth will feel extrusive force and moment that will tip the molar back. Anterior teeth, because we tie the wire anterior to the center of resistance of this giant tooth, we expect the teeth to experience moment of the force, which is away from center of resistance, and this is exactly the same as in case of the intrusion arch that we explained before. But in addition, because when the wire start to twist inside the bracket, when the four teeth try to intrude, the wire will have an angle relative to the slot of the bracket. This will activate the couple inside the bracket. So we'll have another moment of the couple. So here, this makes this system difficult to measure. We cannot tell how much the force felt by the anterior and posterior, and whether these teeth will, how they will react, whether we'll have intrusion or extrusion. But this is the system, and Ricketts is very happy with it, and the people who use utility arch are very happy because they achieve their results, and they don't care whether they intrude or extrude because they use it in children. In children, if we at least hold the incisors, this is considered as relative intrusion. Even if posterior teeth extrude, it's like you are accelerating the extrusion of posterior teeth in the interarch space that will be created by growth because those patients are growing. Okay, then people attempted to prevent flaring because they will be having flaring effect, proclination of incisor, which is sometimes undesirable. People attempted to solve this problem by applying lingual crown torque. So when we say torque here on the incisors, we should distinguish between two. Either if we want to procline incisors, then we call it a crown buccal or labial crown torque, means that we are going to tip. If you want to move the roots of the incisor lingually, you call it lingual root torque. The opposite here, now we want to torque the roots out and the crown in, this is call it lingual crown torque, which is labial root torque. Anyway, if you want to prevent this moment, the two moments, what they do, they create opposite moment, so they will create torque, twist in the wire inside the bracket. So this will counteract the moment of the couple inside, and it's supposed to prevent this movement, the flaring effect. However, when this system was analyzed, it was found that doing this will increase the force level on the incisors and in the molars, on the anterior segment and the reactive segment. So if you increase the force system here, what will happen? Do you think the intrusion will occur? Of course, as we said before, we need light force, so this will never happen. Or we don't know. We don't know actually. And we cannot tell in this system how much the force applied or felt by the anterior and how much force felt by the posterior. Another way of doing this is to cinch back the wire. If you cinch back the wire, as in this case, this will create the same thing, will increase the level of the force felt by the incisor and that felt by the molars. At the same time, will create mesially directed force, which will create tipping the molar. So here also, the moment the force system will be difficult to understand because we will be having another moment this way, and anteriorly, same thing happens, that we will be having additional force, or the level of the force will increase, which is sometimes it's not appreciated in the clinic, but it happens. So this explains why the two-couple system is indeterminate and it's difficult to measure and to predict. So this explains what I said before, exactly all the details I would like to know. How, if we want to flare, to prevent flaring of incisor by applying either torque in the anterior segment or by cinching back, we can do cinch and torque, which will make the effect even more. So both effects help explain why utility arches often produce disappointing amounts of intrusion relative to molar extrusion. If you are not careful with intrusion utility arch, you will not do, as I said, any intrusion. It will be not predictable. When we say predictable, means that we want the results to be the same in every patient we see. This finished the part of the determinate versus indeterminate. Now we're going to talk about symmetric and asymmetric bends. Like in our example, which is 2 units, anterior large giant tooth and posterior giant tooth, and then we want to study what happens between them. Like we have two couple system and we want to place a bend in the middle. So having a bend in the middle will activate the two segments. And we want to see how this will, how the two segments will react, the two groups of teeth. So the bend, it can be placed in the middle as V bend. This is one of the, like in, let's go back a little bit. The types of bend that we use when we do orthodontic treatment, we do either V bend or step bend. We want to see how V bend affects the force system, which the 2 units, as I said, 2 giant teeth, and how the step affect 2 unit system. When we place the bend in the middle, this is called symmetric V bend, in the middle between the 2 units, 2 equal units. So this will create equal and opposite couples at the brackets. So if we have 2 equal and opposite couples, one on the anterior segment and one on the posterior, this means that the force here will cancel the force here, because each couple will create a force in a vertical direction. For example, let's say upward and opposite inward and the opposite in the distance segment, and the other couple will create the same force. So the forces will cancel each other and we will end up with 2 equal and opposite moments, which will tip the teeth away from each other. This is if it's symmetrical V-bend. How to make it? You make it in the middle between the 2 group of the teeth if they are really similar. If we move the bend, the V bend, little bit to one side, then this will create asymmetric V bend that will not apply equal and opposite couples. Example for this, the V bend, the symmetric V bend, is when you have transpalatal bar and you activate it in the middle. This will create equal and opposite moments on the molars, which will help them to derotate in case the molars were rotated lingually. So this will help to derotate them without any anteroposterior movement. This is the example, which is not clinically possible, but if we have 2 molars and we have V bend in the middle, these are 2 equal units and a V bend between them. So this will create, of course, this is 2 couple system. This will create couple here, 2 forces. So each force will have opposite force on the opposite side. So we'll have extrusion intrusion force here and extrusion intrusion force. So each one will cancel each other. We'll end up with clockwise couple here counterclockwise couple on this side. And as I mentioned before, if we have the transparatal bar, we expect by doing symmetric V-bend in the transparatal bar, if it's rigid one, to derotate the molars, the mesial out or buccal. When it comes to our example of utility arch or intrusion arch, because the anterior segment is different inside than posterior segments, the V-bend is expected to be a little bit towards, the symmetric V-bend is expected to be a little bit towards the molar. Let's read here what happened in B. To create equal and opposite couples between two units with unequal resistance to movement, like the molars and the incisor, a V-bend must be displaced toward the unit with greater resistance. So it's not in the middle, it has to come closer to the unit that has more resistance. So symmetric V-bend between incisor and molar would be opposite toward the molar. One must know the approximate anchorage value of teeth or units of the dental arch to calculate the appropriate location. So here, if it's symmetric, but precisely where it's difficult, maybe mechanically we can measure that, but clinically, just you don't have to make it in the middle, a little bit off toward the molars. So if we have unequal and opposite couples, so the net results, net equilibrium forces, would be to intrude one unit and extrude the other one, as we saw in the example of utility arch, which is a two-couple system, when the V-bend made also always close to the molar. So when we make the bend close to the molar or an intrusion arch, this will create an intrusive force on the incisor and extrusive force on the molar. So to make it easy on you, just let's put it this way, that when we do V-bend, we expect the unit that is closer to the V-bend to move in the same direction as the V. So in the intrusion arch, we do the V-bend towards the occlusal, so expect the molar to extrude or go occlusally. The distant unit from that tooth, from the V-bend, will experience the opposite, which is intrusive force or downward directed force. As the bend moves closer to one of two equal units, the moment increases on the closer unit and decreases on the distant one, while equilibrium forces increase. In most studies of the asymmetric V-bend, a location is found where no moment is felt at the distant bracket, only a single force. Now let's see what this is. So when the bend moves closer than this to one bracket, moments at both brackets are in the same direction and equilibrium forces increase further. So let's to make it easy, the location of the V-bend is very important. If you make it in the middle, this will create equal and opposite moments with no force. If you make it closer to one segment, this will create a moment, as we saw in the intrusion arch, two opposite moment on the molar, two unequal forces, opposite, so two equal forces opposite in direction between the two segments, and moments felt by the anterior and felt by the posterior. Usually, the moment felt by the anterior is opposite to the moment felt by the posterior. So as we come closer to the posterior segments, come closer with the V-bend, this might reach to a point where we cancel. So the anterior teeth, the distant teeth, the anterior teeth, will feel no moment at all. And if we come even closer to the posterior segment, this will make or apply moment that is in the same direction as the moment felt by the posterior teeth. So as we come off the center, we expect to have two opposite moments on the posterior and the anterior segment. And we come more closer to the posterior segment, the anterior teeth will feel no moment, and then as we come even more closer, then we expect the anterior and posterior teeth to feel moment in the same direction. So this shows how important it is to determine or locate the V-bend. So the V-bend is sometimes critical. And unfortunately, calculating the position, the precise position of the V-bend that creates what we want is sometimes difficult. So this shows you the V-bend. If you place the V-bend, as I said, off the center, let's say this is the center, you place it a little bit off the center, this will create what we saw in our example, that we can do intrusion on the posterior, on the molar, and extrusive force on this tooth and intrusive force on this one with moment in this direction. But if we come exactly to the 1/3 position, this means the V-bend is away from this segment 1/3 and from this segment 2/3, we will cancel the moment felt by the anterior or the distant unit. And if we come even more closer, so we'll be having two moments in the same direction. So we moved from clockwise moment when it was off the center to no moment when it come to 1/3 position to opposite moment that is similar to the moment on the posterior segment when we came to 1/6 position. So this is very interesting. So just to make it easy again for you, because sometimes we have the V-bend can be applied also in buccolingual direction. So let's put it this way. If we have the V-bend, asymmetric V-bend this way, this means that the segment closer or the unit closer to the V-bend will experience a force directed or movement directed the same direction as the V. And the distant segment will experience an opposite force. All right? Just to make it easy. I hope you understood this. This is another bend that we do between the brackets, very common bend, which is step up, step down bend. So we do steps between teeth. So especially when we want to align, for example, to intrude incisors, theoretically, we try to correct deep bite. Let's put it this way. We correct deep bite by doing step up for the incisors. Mean we come distal to the lateral, we do step up, and then we step it down distal to the opposite lateral. So the wire will be higher than the level of the bracket. So when we insert it in the bracket, this will create an intrusive force on the anterior and extrusive force on the posterior teeth. So if the position of the V-bend is critical the step is critical as the V-bend, no. The position is not that critical. What critical is the height of the step. Even small increase in the height will create a very large force on the felt by the two teeth. And in this example, this is the example that we're going to use. The force system applied only on two teeth, two central and a bend between them. We want to see how these two units will react to this step bend. So step bend which creates two couples in the same. So in general, the step bend will create two couples in the same direction, regardless of its location between the brackets. The V bend was creating two couples in opposite direction if it's off the center. If it's 1/3, it will create one couple on one side, the other one will be no moment at all. And then if we go to the 1/6 position, we expect to have two couples in the same direction. Here, with the step, it creates two couples in the same direction. So this is another important way that the location of the step is not that critical as the V bend. So the location of a step bend has little or no effect on either the magnitude of the moments or the equilibrium force. But in general, it should be placed in the middle because if you make it closer to one of the teeth, it will be difficult to engage. It might break the bracket, so it's better to place it in the middle and where you have adequate inter bracket distance. So let's see how this happens. So If you want to see how this happens, let's say you engage the wire in the first bend, in the first bracket, and then to engage it, you have to raise this wire up to engage it in the other one, because the wire is supposed to come here. Then you have to raise it up. This, when you raise it up, will create the moment. You can tell the couple, the moment of the couple that will be seen on this one. So expect to have similar couple on the other side. You understand? So you put the bracket here, inside the bracket. You put the wire in the bracket, sorry. So with the step, this segment of the wire will be below the bracket. So to activate it, you have to raise the wire up. Raising the wire up will activate the moment on this tooth, and it will be in this direction, which is counterclockwise. So expect this tooth also to feel counterclockwise. So when we try to figure out what happens if we try to step or put step between these two teeth, we expect the two teeth to rotate counterclockwise. So yes, you are going to correct the level of the two brackets, but not by extrusion and intrusion force. You're going to do that mainly by rotating the two to align the two brackets, but in an inclined plane, which is not desirable if we do orthodontic treatment. That's why sometimes we expect to see this, that when we align, we expect to have, or when we do step between the two, between the central, the canine, for example, and the lateral, we do step. We expect the teeth to tip in one direction if it's step up or step down. And to fix it, I recommend to you that you have to remove the wire, define the step again, and fit it in. So to avoid any kind of these couples or to overcome these couples. And what helps us also in our clinical work when we do fixed appliance, because we have multiple teeth, this effect is not that critical because we have multiple teeth and we don't see this effect that much. In an experimental model, when they measured the effect of step on the two brackets, like two centers, with interbracket distance of 7 millimeters. Put the pointer, 7 millimeters, which is equivalent to the force, the distance, interbracket distance between two center incisors with twin brackets, or between narrow canine and premolar brackets, and they place a step bend between, and bend was 0.35 millimeter in height. They found that this bend, small one, 0.35 millimeter, would produce an intrusive and extrusive force of 347 gram on the adjacent teeth, and a moment that is about 1,210 gram millimeter couples in the same direction. So this small bend created this amount of force, extrusive and intrusive force on the adjacent teeth, which means that at the end, if you are intending to intrude a tooth, it will never intrude. What happens that adjacent tooth the tooth will extrude instead of intrusion. So the extrusion will prevail all the time. If you try to make a larger bend, like 0.8 millimeter, it's very difficult to engage. The bigger the step is, the more difficult to fit the wire in, and you end up with either permanent distortion of the wire at the step side, or you might break the brackets. So in clinic, we do bends and we expect it to apply light force, like this system. When we do step, we do a lot of steps, like on a very small wire, which is 16 mil, sorry, stainless steel wire. So even when we do that, sometimes we do unpredictable. We expect we see unpredictable results, like instead of intrusion, we can see extrusion. So that's why using a bends is very critical, and the outcome is not that predictable. So the same experimental model or setup, they evaluated the effect of asymmetric V-bend or starting from the symmetric to asymmetric, with the apex of the bend about 0.35 millimeter above the plane of the bracket. They found that this will produce 803 gram millimeter couples with no net intrusive or extrusive forces at the 1/3 position. So at the 1/6 position, they found that we have intrusive and extrusive forces over 900 gram with very large moments. So the results here also would be extrusion in addition to root movement. So even with the asymmetric V bend, when we go away from the symmetrical position into closer to one segment or to one unit, this will increase even the level of the force. This table. So the experimental model was to bring two brackets with interbracket distance of 7 millimeter, and then they created bend 0.35 millimeter bend in the step and a V bend that is higher than the level of the bracket by 0.35 millimeter, and they wanted to see the effect. For the step, when they did the step in the middle, they found that there will be they found the moment experience, as we said, in the same direction about when they give it 1 as a reference. And when the force generated here, it was similar to the V bend when it started to be asymmetric. And the amount of force felt was around 347, which is a lot in this experimental model. So this is in general, and this is the experimental model. They found the force felt by 0.35 millimeter bend by the two teeth around 347, which is a lot. That's why if you are intending to intrude, what will happen? You will have the opposite. You will have more extrusion than intrusion. And the moment created of the couples, which is the same direction as we said, 1210 per tooth. When they evaluated the V bend, they found at the symmetric V bend, the moment was opposite, about 1. It took the reference of 1, and as we go off center to one segment, the moment will be about 0.3, then it will be -1, -0.30, and then it will be go to the opposite direction. So it will be having moment in the opposite direction. So it will go from minus to positive. And the force also was found to increase as we come closer to one tooth than the other. And this is the model experimentally. These are the results of the experiment. So this is when we apply the V bend or step in interbracket span of 7 millimeter, which is this is very small. So if we increase the span, make it instead of 7, we make it 14, the force level was found to be reduced. So increasing the interbracket distance will reduce the amount of force felt by the adjacent teeth. So 43 instead of 347, and still 43 gram of force is large. So we expect to have mainly also extrusion, and maybe intrusion is difficult to achieve with this level of force. Having long span like 2x4 model, this might make the effect much lighter and help us to do intrusion extrusion, especially when we do V-bend application. That's why having the bypass utility arch is fantastic, that add more or larger range to the wire and make it more flexible or springy. So this is applied also on the V-bend, make the position, the location of the bend less critical when we use long span. That's why, as I told you before, exactly determining exactly the position of the V is very critical, very difficult when we have when we apply or use it in the intrusion arch. But because here this paragraph explains nicely that having this long span will make the position of the V less critical. So we don't expect to see exactly the result that we explained earlier with the position changing along the wire. In addition, with the problem with the 2x4 two-couple system, like the utility arch, the effect is not only 2D, it's 3D. So we expect it to have to be more unknown or more complex in effect. So this makes the analysis of torque bends particularly difficult when we use 3D analysis. And at Saxon, they using the finite element analysis modeling, they found that the results we expect in the 2D will remain valid when we do 3D analysis. So it's very similar. So we're not worried about it that much. I'll give you a chance to read this part. Here, again, another application for the asymmetric V-bend. If you make the asymmetric V-bend, this is what was mentioned in the previous slide. If we make the bend, instead of making it closer to the molar, we make it closer to the incisor. What will happen? This will help us to control the proclination of incisor. It might help us to flare incisors, and if we cinch back, might help us to torque the roots palatally if we do the bend closer. However, because the bend closer to the anterior segment, we expect the anterior segments to extrude rather than intruding, and the distant tooth will have intrusion. If we apply the same rule I told you about, that the tooth closer or the unit closer to the V will move in the same direction as the direction of the apex of the V bend, and the distant tooth or unit will experience force in the opposite direction. So expect the anterior teeth to extrude. So although this is a way to control the proclination of incisors, whether to flare them or retrocline or torque the roots lingually, it has a very critical problem, which is the extrusion intrusion effect. Maybe, let's put it the other way, if I have case with class 2, sorry, with open bite anteriorly, and I want to extrude them, maybe then I can do this, do the V bend closer to the incisors. This will have extrusion force on the inside, so it might help us to do in intrusion and to close open bite, and the remaining problem will be how to control the root and the inclination, the anteroposterior rotation of the incisor, which you can figure it out in a way or another. Appropriate way to do torque instead of flaring incisor and prevent what the consequences of the using of the 2x4 setup is to apply a base arch wire that is heavy and engaged in all brackets except central incisor. Make the wire lower than the brackets. And then, like, for example, in cases of class 2 division 2, where you want to torque the roots lingually, and instead of flaring them, you don't want to flare, you just want to torque the roots lingually. So what happens here, and then you use this spring, that is when it's engaged in the incisors, when this is the base arch wire, engaged in all brackets except the incisors and below the incisors brackets, and then we engage this torquing springs that is engaged in the central incisor brackets, rectangular wire, and then it has helices here, and then this is the arm upward. So when we activate it, we bring it down. This will help. So when we bring it down, we'll activate the couple inside the brackets, and this will help to torque the roots lingually. And to minimize any flaring effect, we can cinch the wire back. So this is more appropriate to do torquing on the incisors. This explains what I said. Give you a chance also to read how we can use two-couple system to change the inclination of incisors in a better way than doing it with 2x4, like in the example of class 2 division 2 malocclusion. Okay, there is another application which is to correct posterior crossbite. Usually, when we want to correct posterior crossbite, dental posterior crossbite, we do expansion with palatal appliances like quad helix or transpalatal in the mild cases, transpalatal bar. And sometimes this is annoying to patients. Is there a way that we can correct it without using any palatal appliances? Yeah, there is a way suggested by Mulligan to do 2x6 configuration, which is attached to the 6 anterior teeth from canine to canine, and then to the molar. Then you apply in between, you apply the V-bend. So first of all, this is a two-couple system, and the V-bend will be applied to move the molar out. And let's apply this on the model. This is the model that we want to do. Apply 2x6 wire engaged, rectangular wire, of course, heavy wire. Engage the wire completely in the canine to canine, and then do the V-bend. Here, if you imagine with me, with the arch form, the wire will go passive in the bracket from molar to molar if you have the proper arch form. If you create a V-bend here, so this segment will go out, right? V-bend, the apex directed palatally. This will move the wire out. How does this configuration? And this is two-couple system. So the V-bend is closer to which segment? To the anterior segment, and it's directed palatally. And the distant segment, the distant tooth will be the molar. So what will happen if when we do the V-bend in this direction, and the wire will go out, the teeth adjacent to the V-bend will experience movement in the same direction as the V-bend, correct? As we said before, same direction as the apex of the V-bend. So expect the canine to canine will experience, or the canine mainly will experience lingually positioned force or lingually directed force, which will be stabilized because we are holding all teeth together. We are having anchorage from all other teeth. The distant tooth from the apex from the V-bend will experience movement opposite in direction, which is outward, buccal in direction. So by doing so, this will create for us buccally directed force, which will move the molar out, and we call this outbend. Okay, we bend the wire out. If we can do something different, we still can do the same configuration, but with a V-bend closer to the molar. If we make the bend closer to the molar here, what will happen? Of course, the V-bend apex should be directed in the opposite direction, buccal. So when we have it buccal, the tooth closer to the V-bend will experience what? Will experience buccal force, same direction of the apex, and a moment to derotate the molar. So if you have a molar that is palatally positioned and rotated the mesial end, then maybe you can have what we call toe end bend. If you want to do just buccal movement of the molar, you can do this figure in A. So this explains to you how the V-bend can be applied in all 3 dimensions, and it's very convenient. However, I'm talking you can do this, but in simple or mild crossbite, not severe ones, because severe ones to disarticulate the teeth and move them out of the occlusion to the buccal is difficult, and you require a larger level of force. Also, lingual arches can act as 2 couple systems. If we have lingual arch that is, I can also skip this slide to explain. This is a lingual appliance which we call transpalatal bar. So if you look at it, we can the transpalatal bar we in this example is a removable one that has Gashgerian or tube from the palatal. You weld them on the palatal of the molar bands, and then you make this wire, rigid wire without any loop in the middle. So when you activate it, if you want to do symmetrical V-bend, you do bend here and bend here. And then when you engage it, this effect is similar to symmetrical V-bend, as if you are making the bend in the middle. So making the activation on the side symmetrically is called symmetrical V-bend. So doing so will rotate, as I said, it's going to be symmetrical V-bend. So the 2 teeth will experience no anteroposterior forces. So we don't expect the molar to move because each force will cancel the other. And what we expect to have is to have mainly rotation, derotate the molars out. If we do only one side bend, we do toe in on one side, on the right molar on your side. This is like a symmetric V-bend that is closer to the molar on the right. So what will happen? This tooth will experience mesially directed movement, which is in the same direction as the V-bend, and derotation out. The opposite one will experience distal movement without any derotation. Does this have application? Yes. Sometimes we need to move one molar only back a little bit to distalize it, and like mild subdivision on one side. Maybe this could help you to move the molar back on one side if you have adequate anchorage on this side. If to avoid the mesial movement, the molar, you can add the premolars all in one wire, then you can move this back a little bit, you create some space. Also, by derotation, we can also create some space, like, and this is just, I'm talking about distalizing effect. And of course, this is if you have 2 molars mesopalatally rotated and you want to derotate them in cases like class 2 cases where you have the molar mesially rotated. So by doing so, this can help you to gain some space if you derotate the 2 molars back. The author is discussing the possibility of distalizing molar on one side using transpalatal bar or even bilateral, and he's saying that it's not really feasible and possible because it's been promoted for that you can do distalization on one side and then stabilize that side and do distalization on the other side. So you do one molar at a time if you want to distalize bilateral. However, the evidence indicates that significant distal movement beyond rotation, significant distal movement beyond rotation of buccal segments is unlikely. What happened? The opposite is possible. Mesial movement is easier, so expect the teeth on the opposite side to move mesially. So it's not a practical way to distalize bilateral. Maybe unilateral one side, maybe you can do just to derotate molars or just distalize a little bit. Also, another application for the transpalatal or lingual arch is to do torque movement and to do expansion, differential expansion. Let's see this example here. When you expand, you can see the amount of expansion with the red dots here, dotted line. you can see that when we apply the force, because we are lower than center of resistance on both molars, we expect these teeth to move buccally. At the same time, they will tip due to each one of them will experience moment. This is clockwise and this is counterclockwise. They will tip buccally. To overcome this, maybe we can apply another moment. So we activate the couple in the bracket, in the tube, sorry. So when we do that, V bend here and V bend here, this helps to apply another moment of the couple that will cancel the moment of the force. And it has to be large enough to resist the flaring effect. If you want to do just expansion, bodily expansion. And sometimes if you want to do just bodily expansion, unilateral expansion, what you do V bend on one side, so you activate the moment of the couple on one side. This will allow this to tip, to experience more of tipping movement, so repeating bodily movement of this tooth against tipping. So of course the tipping will prevail and expect the tooth to flare. And the author is suggesting that if you make this wire round instead of rectangular, this might help to apply more tipping movement, but I don't understand how, if this is vertical slot, which is not very clear to us here if it's vertical slot or not. But if it's horizontal slot, yes, he's right. But vertical slot, it doesn't make a difference if you make it round or rectangular because the wire still will touch the tooth in 2 points. Angerval and co-workers have shown quite convincingly significant expansion on the tipping side, which can be produced perhaps more effectively if the appliance is converted to one couple device by placing a round rather than rectangular wire in the bracket on the tipping side. A somewhat unusual application of lingual arch would be to tip one molar distally, uprighting it. The reciprocal force, of course, would be mesial tipping of the opposite molar. This activation would require a twist in the lingual wire. The location of this twist bend is not critical. The relative moment on the molar teeth will be equal and opposite wherever the twist bend is placed. What is segmented arch mechanic? In orthodontics we used to have, or this is a technique that was developed or introduced long time ago, which was also introduced by those people who introduced biomechanics. So the idea behind it was to do predictable tooth movement. How do you do that? You divide the teeth into segments. For example, if you want to do extraction case, you want to do all the anterior teeth together as one segment, and the right buccal side is as the second segment, and the other side as the third segment. And then after aligning and leveling in each segment separately, then you hold them together, hold the buccal segments together with lingual arch or transparatal bar, and then you intrude or correct the vertical relationship of the two segments together, and then you close space. And mainly they apply one couple and two couple system for most tooth movement. So they can be able to analyze the force system applied, and they want to do predictable outcome results. Typical segmented arch treatment would call for initial alignment within the anterior segment and posterior segment. So we start by extraction, and then align anterior segment alone, and then posterior segments each one alone. And then after that, if you want to do your anchorage, you set up your anchorage, adding second motor, and decide how you are going to close the space. And then you do vertical leveling if you want to do intrusion or extrusion to make the two segments, buccal segments and anterior segments, the same level. And finally, you do space closure with differential movement of anterior and posterior segments using the T-loop. I think I explained that to you before, doing in mass retraction with different, as we said, the position of the loop will affect the type of anchorage that we apply, and it varies between maximum, moderate, or minimum anchorage cases. Sliding usually is avoided in this technique. Why? Because resistance to sliding hampers efforts to control anchorage and introduces uncertainties into the calculation of appropriate force level. Do we use continuous arch wire? Yes, at the end for the final stages for leveling, we use arch wire. But the idea here with the segmented arch mechanic is to do predictable outcome. They want to achieve exactly the outcome that is planned for. Not like the continuous arch wire mechanics that we do, where sometimes we just run wire, we don't know what will happen. And as I explained to you, sometimes we plan for intrusion, and what happens is extrusion, an opposite reaction. So these are the advantages of the segmented arch mechanics, which is the main advantage to give you good control and give you predictable outcome. And sometimes you can do movement that you cannot do with continuous arch wire. Disadvantage, however, the complexity. It's very complex appliance. Single arch, TPA, and you do a lot of wire bending, and sometimes it's not acceptable by the patient and takes longer chair side time, takes long time, and we're not sure how the outcome to be different than just continuous arch wire mechanics. Example, simultaneous retraction and intrusion. Why it's important? Because most of the time when we do sliding and in-mass retraction, what happens that we expect the incisor to tip while we're tipping them or moving them lingual. They will tip and the incisor might extrude a little bit, which is sometimes considered as undesirable effect. So what is designed here? Let me show you here the design of the appliance. Of course, they extract and then align buccal segments as I said. You have to have TPA or lingual arch. The lingual arch made should be away from the incisor so it allows their movement lingually. It's not meant for anchorage. And then you stabilize the buccal segment with heavy wire and the anterior segment, and then you have hook here and an auxiliary wire, intrusion wire, is then activated to retract. So it retract by cinching, so this will help to retract at the same time intrude. And look at the level of the force, line of force. It's almost close to center of resistance to reduce the tipping effect on the teeth. This approach helps to retract at the same time intrude. Nowadays, with the introduction of mini screws, such applications are not valid because we can do all of these movements. We can do simultaneous retraction and intrusion with mini screws. If we place studs here, or we hold, if we can place studs here, we can do intrusion and retraction at the same time without losing anchorage. So mainly nowadays, nobody's using segmented arch mechanics at all. But in general, we should keep in mind that segmented arch mechanic sometimes it's useful to understand our fixed appliance. Like you can use utility arch. You can do intrusion arches. You can do utility arch with make it one couple system, or intrusion arch one couple system. So understanding the biomechanics is very important for you to improve your practice and try to produce or make predictable outcome. Complex segmented arch mechanic carries with it two other potential disadvantages that must be kept in mind. First, even with the most careful engineering analysis, it can turn out that something was overlooked in the determination of the likely outcome. The application of engineering theory to orthodontics is imperfect enough that a unique force system for an individual patient may not produce the expected outcome. So when you try it clinically, this is engineering. On papers, yeah, this is something good. But in clinic, sometimes the outcome is not the same. Second, most segmented arch mechanics contain little or nothing to control the distance that teeth can be displaced. If something goes wrong, a precisely calibrated springs with a long range of action encounter something that distort them. For example, patients distort the wire, major problems can occur. The mechanical efficiency of a segmented appliance can be both an advantage and a disadvantage. So unless you have a good patient and you are really top of your case and do follow-up, good follow-up, those cases might have other side effects that are not planned for. What about our mechanics, continuous arch mechanics? So our mechanics, we call it continuous arch mechanics when we use continuous wire from molar to molar. Engineering analysis of the effect of continuous arch wire, one that is tied into, as I said, brackets on all teeth, is essentially impossible. So if you want to analyze the results, it's not possible. All that can be said is that an extremely complex multi-couple force system is established when the wire is tied into place. The initial result is a small movement of one tooth. As soon as that occurs, the force system is changed and the new system causes a small movement of another tooth, and so forth. Either way, the result is still another complex force system which causes another movement, leading to another change in the system, and so on. So here, what we mean that still our continuous arch mechanics, which is much easier than segmented arch mechanics, still it is unpredictable. The outcome is unpredictable and complex in nature. So we run wires, but we don't know exactly how the teeth will react. And this system changing every time and then when we have small increment of movement. So you have to be careful with the continuous arch mechanics. Continue talking about the continuous arch mechanics and how the results are not predictable, and usually expect, sometimes we would love to see tooth movement, smooth tooth movement over our period of treatment. However, this is not the case here, and even continuous arch mechanics has advantages and disadvantages. So the advantages and disadvantages, they are opposite of continuous arch wire. Mechanics are opposite to those of segmented arch mechanics. They are easier to use, easier on the patient. However, the force system and the moments are not known and not predictable, and we expect to see some opposite results for what we want to do. So, in general, nowadays most of the people use continuous arch wire mechanics, continuous arch mechanics, and few may be still using segmented, I don't know, but the author here giving a nice conclusion that in modern orthodontics, often the clinician must evaluate, the second paragraph here, must evaluate the trade-off between segmented and continuous arch wire approach to specific problems. For those who use primarily the segmented arch approach, Some use of continuous arch wire might simplify your life, and for those who use primarily continuous arch wire, some use of the segmented approach is necessary to meet specific objectives. Quite literally, you consider the benefits versus the cost, time, and risk and make your choice. By this, we conclude this difficult chapter, and I hope I simplified it for you guys. I just want to make sure that you understand what type of book review is this. This is basically it's a comprehensive review tailored to the beginners in orthodontics or whoever read the book for the first time. So I'm explaining it word by word most of the time. I'm copying and pasting all these paragraphs from Proffit book, which is this is the reference, and I'm trying to explain them in details so people can understand this wonderful book that really this is the one and only book that I think is good for anyone who wants to learn orthodontics, and especially this chapter, it gives you in-depth informations about the biomechanics, the force system, the moments, and how we apply them, and how to make predictable outcome, and history of orthodontic appliances when it comes to segmented versus continuous arch wire, the types of wires that are used in orthodontics, their elastic properties, the stress strain curve, and all the definition that you should know about this. Thank you very much, and this is at the end that you subscribe and like the lecture. So because I'm going to continue posting the other chapters of this book. Thank you once again.